Good day, everyone. We're reviewing Wetzel's Limnology textbook, and this is edition number 4, and we're on chapter 6, where we are reviewing lights in inland waters, and more specifically, we are in subchapter 2, at the water surface. Not all of the water radiation that impinges upon the surface of a water body penetrates the water. Surface reflections after the direction of light and snow alter the direction of light and snow, and ice covering the surface can reflect and absorb solar radiation. These losses mean that the amount of light underwater can be substantially lower than that incident at the surface. Reflection and albedo. A significant portion of incident light is reflected from water body surfaces and is lost from a system unless it returns to the water after being backscattered from the atmosphere or surrounding topography. The extent of reflectivity of solar radiation varies greatly with the angle of incidence, the surface characteristics of the water, the surrounding topography, and the meteorological conditions. So why don't we look at figure 6-3 here. So conceptual diagram of light impinging on water and interacting with optically active substances underwater. So we have theta alpha and theta omega are the zenith angle of incidence and refractions. So we have the theta omega here, or theta W, and then we have the theta alpha, so we have the light coming in at this angle, and then the light being backscattered, part of it inside the water with an angle of theta W from the vertical, and then we have the light being then scattered out above the water to that angle, to the angle of theta alpha. So are the zenith angle of incidence and refraction respectively, and are related to the refractive indices of air and water by Snell's law. Ice is usually highly scattering due to air bubbles and the presence of snow. In addition to pure water, chromophoric, dissolved organic matter, CDOM, algae, and non-algal particles, NAP, are the primary optically active substances in most inland water bodies. CDOM strongly absorbs light. So that means dissolved organic matter, you can see here, absorbs light. There's no light that is refracted from it. And then algae absorbs light and are weakly scattering it. You can see that some scattering. And NAP is weakly absorbing and strongly scattering. So we have a lot of scattering in this case. The reflection R of unpolarized direct sunlight as a fraction of the incident light is a function of Fresnel law, which is R is equal to half of the sinus square of this fraction and over the sinus square of this fraction plus the tangent square of this to the tangent square of that, where I is the angle of incidence, the zenith angle of the sun, and R is the angle of refraction, the angle of the light transmitted into the water. The angle of refraction can be calculated using Snell's law, and the refractive index of water, NW, is 1.33, relative to air, which is 1.0. The zenith angle can be calculated as a function of latitude, solar declination, which is affected by time of year, and hour. The albedo describes the ratio of reflected to incident in radiance. An albedo of 0 describes a surface that absorbs all incoming energy, and an albedo of 1 describes a surface that reflects all incoming energy. The reflectance of a flat water surface with the sun directly overhead is about 2%, which equates to an albedo of 0.02. Reflectance increases rapidly as zenith angles approaches 90 degrees. An average reflectance loss value of 6.5% is common, but there is substantial variability throughout the year and with latitude. For example, albedo can exceed 30% in January at high northern latitude, where it remains under 7% all year near the equator. Reflective losses can also be lower if surrounding vegetation or topography, mountains for example, moderate low angle radiation, surface waves can increase reflectance. The increase can be as much as 20% at zenith angles over 60 degrees, but the effect is small when the sun is close to directly overhead. Qualitatively, light in the red portion of the spectrum is reflected to a slightly greater extent than light of higher frequency, particularly at low angles of incidence. So once again here we have light coming in, we have light being refracted, and then light being reflected, and then this is how light behaves in different types of compounds. Ice and snow. Light transmission through clear, colorless, so-called black ice is similar to that through liquid water from the ultraviolet to mid-infrared wavelengths. Indeed, the refractive index of ice 1.31 is very similar to that of water 1.33. However, most ice includes air bubbles that scatter solar radiation, and ice is often covered in snow. Molecules in air are not incorporated into the ice crystal lattice upon freezing and therefore come out of solution as bubbles, which are frequently trapped between crystals as ice grows. Dense concentration of air bubbles in ice, so-called white ice, as well as cracks scattered light. In turn, this reduces light transmission and increases reflectivity. So this is surface reflection, figure 6-4, is surface reflection and backscattering as a percentage of solar radiation at angles of incidence varying from the horizontal, A, clear cloudless conditions, B, reflection of diffuse light under more moderate cloud cover, and C, heavily overcast conditions. So on the x-axis we have the surface reflection, and on the y-axis we have the angle of incident light. So as the surface reflection increases, the angle of incident light decreases. So we have high reflection for light that is directly above compared to light that is coming in at an angle on the surface. Then we have the same kind of condition. However, this is, as the text is saying, a reflection in diffuse light under moderate cloud cover. And then this is in heavily overcast conditions. So in heavily overcast condition, we can see that there is not much surface reflection compared to a day where there is no overcast. During ice-covered periods, the overall amount of reflectance, albedo, absorbance, and transmittance through a lake surface is often regulated more so by the presence versus absence of snow cover on top of the ice and snow texture than by ice itself. For example, in a study of a perennially ice-covered Arctic lake, only 0.45% of incident PAR was transmitted through 2 meters thick ice and 0.5 meters thick snow cover. Removal of snow increased underwater PAR by 13-fold and UV by 16-fold. Coarse-grained snow typically has a lower albedo than fine-grained snow because incident light travels a longer distance between crystals and is therefore less likely to be reflected. The presence of white ice and snow can delay ice off due to its high reflectivity. However, even slight snow melt causes a rapid increase in grain size, which decreases albedo, while freshly fallen snow generally has a high albedo, greater than 0.8. Once snow begins to melt, the albedo can fall to 0.2 to between 0.2 and 0.5. Melt pools on top of ice also substantially increase overall transmittance. Overall, the thickness of snow and ice can vary by as much as a factor of 2 within short distances, less than 25 meters, and lead to considerable patchiness in both reflectance of light and the amount of light underwater, light attenuation in the water column. Light that penetrates through the atmosphere and water surface is available to do physical, chemical, and biological work in aquatic ecosystem. Different wavelengths of sunlight participate in or regulate a range of ecological and geochemical processes. The spectrum of light underwater differs from the spectrum of light reaching the water surface and is highly dynamic across space and time. The reduction of light with depth as it is absorbed and scattered by constituents in the water column is referred to as light attenuation. spectral and temporal variability in light attenuation underwater can have as large or larger effect on the total amount of light than variability in atmospheric or surface processes, inherent optical properties. The absorption coefficient, scattering coefficient, and volume scattering function are inherent optical properties because they depend on the concentration and characteristics of the substances in water and not the geometry of the light field. The fraction of light absorbed or scattered divided by the layer thickness, also referred to as path length, is the absorption coefficient A or scattering coefficient B, respectively. The volume scattering function describes the angular distribution of light that is dispersed after being scattered. Another inherent optical property is the beam attenuation coefficient, or C, which is the sum of A and B, and represents a fraction of incident light that is absorbed and scattered divided by the layer thickness. These coefficients have units of 1 over length and are typically expressed as per meter, meter to the minus 1. Light scattering is the result of the deflection of light by the molecular component of the water and its solutes, and often to a larger extent by particulate material suspended in the water. Scattering increases in the path length of a photon, increasing the likelihood of it being absorbed. Backscattering toward the surface can result in photons leaving a water body. Scattering of light in a spectrally dependent process is a spectrally dependent process, meaning that wavelengths have different associated scattering coefficient, or C to the lambda. Scattering coefficient generally increase exponentially with decreasing wavelength. However, the exact spectral shape of scattering is greatly influenced by the geometry and composition of the particulate material suspended in water, and total scattering is influenced by the concentration of particulate material. As the quantity and size of suspensoids increase, longer wavelengths are scattered preferentially. Glacially influenced lakes, rivers, and coastal zones often contain high concentration of glacial fluid that is highly scattering, giving these water bodies a milky or opalescent color. A significant amount of light can also be reflected and scattered from sunlit sediment. Sediment rich in calcium carbonate, marl, reflects considerably more light than dark-colored sediment of high organic content. Hard water lakes with high concentration of suspended calcium carbonate particles characteristically backscatter light that is predominantly blue-green. Water bodies which is rich in suspended organic material appear more green or yellow. In oligotrophic water bodies, oligotrophic means nutrient poor, water appears blue, in part because blue light is the shortest visible wavelength backscattered that is detected by the eye. However, in reality, UV, which is not detectable by the human eye, scatters more than visible light. Light scattering can vary substantially with depth, season, and location in a water body, and in response to variations in the concentration or sources of particulate matter. For example, particulate matter can become concentrated in the middle zone of great density change, for example, it's called the metalimnion, or the thermally stratified lake due to reduced sinking as the particles encounter increased water density or as a result of the development of large populations of plankton. While scattering from algae and other organic particles is usually low, it can increase in these layers. Scattering can also increase markedly in areas of a lake where wind-induced currents and wave action agitate and temporarily suspend littoral and shore deposits of particulate matter. When dimectic or amectic lakes undergo complete circulation, a significant portion of the recent sediments of the lake basin are brought into resuspension and can affect the scattering properties of the lake for weeks. Similarly, the variable influxes of suspended inorganic and organic matter from stream inflows to reservoirs can radically increase the scattering of light non-uniformly within the lake basin. For example, cold or saline silt-laden river inflows can move as subsurface density currents along the metalimnion or the apolimnion far out into lake or reservoir. So when we're talking about limnion, we're talking about the strata of the lake, like the zone associated with depth. So the metalimnion is the middle depth of a lake. The epilimnion is the upper depth of a lake, and then the hypolimnion is the lower depth of the lake. These alterations in optical properties can be short or long-lived depending upon the composition and density of the material and the density characteristics of the water column in the recipient water body. Absorption is an inherent optical property defined as diminution of light energy with depth by the transformation of light to chemical energy or heat energy. Absorption of light energy by atoms and molecules occurs when the electrons of the atom and molecule resonate at frequency that correspond to an energy state of a photon. In the collision of an electron and a photon, the electron gains the quantum of energy lost by the photon. The energy transferred by absorption breaks chemical bonds and supports photosynthesis via generated electrons. Light may be absorbed by water, dissolved substances, or particulate substances, while scattering is predominantly a function of the concentration and characteristic of particulate matter. Absorption is primarily a function of dissolved substances, although organic particles such as algal cells can be important in some circumstances. See optically active substances subsection below. Absorption typically increases rapidly with decreasing wavelength. Light absorption is typically measured in a spectrophotometer by measuring the absorbance of or optical density D, which is defined as the base of the 10 logarithm of the ratio of the incident light intensity, I-O, to the light intensity, I, transmitted through a water samples. Beer's law describes how absorbance is proportional to the concentration of a solution. Lambert's law describes how absorbance is proportional to the path length of light through a medium. These laws are often combined, and the resultant Beer-Lambert law is used to calculate the wavelength-specific absorption coefficient, R lambda per meters, as 2.303 coefficient to convert log 10 to natural logs, multiplied by the measured absorbance D divided by the path length L through the medium. In some literature, the term absorption coefficient takes a decadic form, i.e. absorbance normalized to path length, where alpha meters to the 1 over meter is equivalent to D over L, whereas here and in other literature it takes a Napierian form. A is equivalent to alpha by a natural log of 10. So kind of like to summarize here the different processes we have with light, which is a little kind of challenging at times, I think, is we have, so let's look at that figure we were looking at here. So we have, once again, we have light coming in, we have light being absorbed through a medium, and so right here we have light absorption, and then we have a light being reflected, and then we have light being scattered through the water. Okay, so we have an angle of that light being scattered, another angle of that light being reflected, and then we have like different behaviors of light being either scattered, absorbed, or reflected. Thank you.